Welcome back to ECE 501B. Homework number 7 is due tomorrow if you haven't already completed that, and your project is due the first or at the end of the first week of December. You'll probably have a homework assignment number 8. I'll try to make that so that you can enjoy your Thanksgiving break with an assignment in hand. I know you probably will feel lonely if you don't have something to stare at besides the project. Today what I want to do is push further into or through chapter 7, and we will quickly review what we've introduced relative to positive operators. And in black is really what a positive operator is. It has these two properties, but when you think of a positive operator, you might think of scaling, contraction or expansion, and that's what we're wanting to accomplish or sort of convey with this notion of a positive operator from Theorem 727. Once we had that, we finished up, I think, last time by stating Theorem 28 in Chapter 7, which was dealing with this unique positive square root. If we do have a positive operator, we can create a unique positive square root for that positive operator. And we will then give an example of that in the matrix form. We'll look at how we could construct a square root. Then we will introduce isometries. And those are these operators that preserve the norm. If you have the norm of a vector, that's equal to the norm of that operator applied to that same vector. And if you look at that, the only way that that can be 0 is if the vector v is the 0 vector, which really means that that operator, that isometry, is injective. It has a trivial null space, the only way that this is going to be valid. So this isometry is an injective map by definition of that norm preservation property. And you can think of, when you hear isometry, you can think rotation, just like when you hear positive, you can think scaling. Now, where are we moving and how far are we going or shrinking in that direction that we rotated? So we're trying to break an operator down into these two pieces, a scaling piece and a direction piece. Just to plant the seed, just like a complex number, you can represent a complex number in polar form. It has an angle and a magnitude and an angle for a complex number in polar form. We are trying to generalize that concept to a linear map. And then we'll get into, obviously, this polar decomposition, which is exactly that analogy. We're now thinking of something consistent with a complex number written in polar form. Now it's a linear operator. We're going to write that in quotes in polar form. We will find its scaling piece and we will find its direction piece. We'll separate this operator into two pieces, a positive operator and an isometry. It's scaling and direction. That's the idea. Meaning we need to get comfortable with positive operators, and that then is a linear map that has these two properties. It's self-adjoint, meaning it equals its adjoint, and it has this positive nature when that operator is applied to any vector in the underlying inner product space. Its inner product, let's say the input vector v, inner product with the output vector tv, is always going to be positive, or I should say non-negative. Theorem 727 gave us this equivalence of multiple statements, 5 statements. T is positive. That's equivalent to T is self-adjoint, and it has non-negative eigenvalues, which is equivalent to T having a square root, where that square root is positive, which is equivalent to t having a square root that's self-adjoint, which is equivalent to saying there exists a linear map S, which when pre-operated on by its adjoint, or t can be factored into S adjoint S. Those are all equivalent statements. If you have one, then you have any of the others. That's theorem 27. We finished up last time with this proposition, proposition 728, which says that every positive operator, so if you have a positive operator, which means it's self-adjoint and it enjoys this inner product characteristic, then you can find or you can get a unique positive square root for that positive operator. And we really sort of created that square root during the construction process when we were proving theorem 27, when we were proving that B, statement B, implied statement C. That relied on us creating this square root. So let's now look at an example for a matrix. Suppose that we are given Q sub 2, and actually we've already worked with this according to my notes. So I'm saying that we have already shown that the matrix Q sub 2 is in fact positive. It's obviously self-adjoint, and if you computed the eigenvalues of that, they would both have to be non-negative. And if we did that, if we computed, and so a part of this creation or construction of a square root of the matrix Q sub 2 is going to rely on finding the eigenvalues of that matrix. The eigenvalues of that matrix, one is at 1.58579. So although we started with this nice looking matrix, its eigenvalues are not necessarily nice numbers if you think of nice being integers or something kind of limited in terms of their significant figures. And the other value, eigenvalue is 4.41421. And now let me label those. This I will label lambda sub 1, and this is lambda sub 2. And that will be important because we are going to associate with each of those eigenvalues an eigenvector. And because this matrix is symmetric or self-adjoint, it's real and symmetric, so it's self-adjoint, we can now find orthonormal eigenvectors for that matrix. And the eigenvectors again, these are the eigenvalues and the eigenvectors of Q sub 2. Let me just write those down as in being the columns of a matrix capital X. The first column is minus 0.92388. Obviously, I'm limiting this to a certain number of significant digits. And now the second entry is minus 0.382683. The other column is 0.382683, and the second coordinate of the second column is minus 0.92388. Where this first column is the eigenvector associated with lambda 1, the second vector in capital matrix X is associated with the second eigenvalue, lambda sub 2. And in fact, these vectors form an orthonormal basis for our vector space. And what's a basis require? Just to remind ourselves. They're linearly independent, which it looks like they are. They're not in the same direction. And they span the space. And our space isn't very big right now. It's R2. So it's a two-dimensional space. They point in two different directions, and they are linearly independent. If you looked at this and somebody said, oh, and that's not supposed to be a dagger, that's supposed to be a T. If I computed this product of X times its transpose, what's the result? It's the identity matrix, because these are orthonormal. These vectors are not only orthogonal, but they've been normalized to have a length of 1 in the Euclidean norm, meaning E1 times itself is going to be 1, or the norm of E1 is 1, the norm of E2 is 1, and their inner product, I think you can see, if you inner product E1 with E2, you're going to get 0. If that's the case, X times X transpose is the identity, then X transpose is really the inverse of X. So now that we have an orthonormal basis, if we wanted to invert that, that's pretty easy. All we have to do is transpose that matrix, and we get the inverse, which is a little easier than the normal computation of a matrix inverse, if you remember that algebraic process. All we've done so far is identify the eigenvalues and the eigenvectors, and these eigenvectors are actually normalized to have a length of 1. Now that we have that, let's now create, reminding us what we're trying to do. We're trying to find a square root of q sub 2. So let me call, keep me honest, I may forget. That's just a matrix, S sub q. That's going to be our square root matrix, but in a minute I'm going to be using S for the isometry, and I thought maybe I shouldn't be calling this an S. You'll get things confused. So this is S sub q, so to square root. So S sub q, E1, define that to be the square root of lambda 1 E1. So we haven't said what S sub q is. We're going to build it up based on this relationship and the other relationship, which says we want S sub q to be doing what? When I say that S sub q E2 is the square root of lambda sub 2 E sub 2, what am I really saying about S sub q? Or what are some words that I can use to describe this linear operator, S sub q? If I apply S sub q to E1, and now it gives me a scaled version of E1, that's all I'm saying, then E1 is invariant under this map. And so is E sub 2. Or you could think of these as, these are really eigenvalue-eigenvector relationships, where the eigenvalue now is a different positive number. It's just the positive square root of lambda sub 1, and lambda sub 1 was the eigenvalue of q sub 2. Remember, we're trying to build up the square root of q sub 2. These square roots then seem to be okay, or sort of intuitively reasonable as far as putting them there. Now that we have this, again, we haven't done anything. We've just created or identified sort of a placeholder, a variable, which is a matrix, S sub q. We haven't put anything in it yet. But let's now see what happens when we say, okay, take S sub q and now post multiply it by E1, E2, which now turns out to be a square matrix. And that now needs to be equal to, or that's equal to, based on the earlier two equations, that's equal to a scaled version of E1 and a scaled version of E2, and we can scale those by the appropriate scaling factor by post-multiplying E1, E2 by this diagonal matrix with these square roots of lambda 1 and lambda 2 on the diagonal, where this is our matrix X on both sides. Well, now we know capital X, and we know these square roots of these eigenvalues. Everything is known except for that matrix S sub q. We can hit both sides on the right by the inverse of capital X, or X transpose, and we will have defined S sub q. Now the left-hand side, S sub q, is written in terms of matrices that we now have every piece available to us. And so we've now constructed this square root matrix. We can now write S sub q. This matrix is now X square root of lambda 1, 0, 0, square root of lambda sub 2, X inverse, which, if you wanted to, this is just X transpose, and that's equal to 1.3825 minus 0.297593 minus 0.297593 and 1.97774. And in fact, if you now looked at S sub q, what did we start with? We started with q sub 2. That's now S sub q times S sub q, or S sub q is a positive square root of q sub 2, and we were able to build that up knowing or being able to identify the eigenvalues and eigenvectors of our original matrix q sub 2. So given a matrix q sub 2 that's positive, we can create this square root. And that's what the proposition 28 said is possible. There's now our positive operator, and if we're given a positive operator, we can find a square root, which we may want to do eventually. Now let's get into the next topic, which is associated with direction, isometries. These are beginning to be discussed on page 147 of the book, and here is the description of an isometry. An operator, S, I told you I was going to use an S, so that's why I was trying to use S sub q before, that's a linear operator on our inner product space V, is an isometry if SV is equal to V, so the norm of SV is equal to the norm of V for all V in our inner product space. We can make some particular observations relative to that definition of an isometry. One is that these isometries preserve the norm, or are norm preserving, and they essentially are a generalized rotation or direction. let's now dig a little bit deeper into what this is or what we have. Here's an example. Let's let S be a linear map on this inner product space V with S E sub j equaling lambda sub j E sub j, and these E sub j's are coming to us from a list where that list is an orthonormal basis. So we're using the same notation that we've always used for an orthonormal basis. So this relationship of this operator S is such that we can have S e to the j equal to the lambda sub j e to the j for some orthonormal basis. E1, E2, E sub n on our inner product space V. And we want to see what that sort of means relative to these eigenvalues lambda sub j is what we're trying to show in this example. So does this, if S is in fact an isometry, does that imply a certain property on these lambdas, on these eigenvalues? Since this is now an eigenvalue, eigenvector equation. If I now give you a generic vector, v, little v, in the vector space, I can decompose this vector as a linear combination of, or I can, how do I want to say this? I can now decompose v as a linear combination of these basis vectors. Meaning I find the projection of little v in the direction of E1, and that's going to scale E1, and so on down to all the different basis vectors. Or I can write v as v inner product with E1, that's just a scalar, time, or that's going to scale now this orthonormal direction E1. I can do that for all of these orthonormal vectors. If that's the case, what's the expression for the norm of v squared? And now think back to what we've done before. If you just said, and mentally, if you just pictured this, you could say each of those inner products, let me call them an A. The first one, let me call it A1. That's A1E1 plus A2E2 plus dot 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 plus A sub n En. Now, what's the norm squared of V? That was a theorem or a proposition, wasn't it? What would be on the right-hand side, or how could we rewrite that norm in terms of maybe pieces that are in that expression for that decomposition of V? Do you remember? Take the absolute value of each of those coefficients and square it, and then just add all of those squared absolute values up, and that will be the norm of V squared. Does that sound familiar? Because E1, E2, and En, what is their impact on a magnitude? Nothing, is it? It's just one. It doesn't scale. So that now if I called this first piece A1, I'm now saying take the absolute value of VE1 and square it. And add that to this coefficient scaling E sub 2, which is VE sub 2. Find its absolute value and square that. Plus, dot, 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 plus the absolute value of VE sub n squared. So if we've decomposed a generic vector v into these scaled versions of our orthonormal basis, then each of those scaling values we can use to define the norm of v squared. That's just a standard result of what we've already talked about. What if we now do that for little v, this same little v, but now operated on by this matrix capital S, or this operator capital S? So let's do the same thing for SV. Meaning, if I now have S times V, but if I've already decomposed V into this algebraic sum of basis vectors, where those basis vectors are weighted by these inner products, those inner products are just scalars. Those can slide through this operator S, meaning SV could be written as the inner product of VE1, that's just a scalar, times SE1, plus the inner product of VE sub 2, SE sub 2, and we can just keep doing that, VE sub n, SE sub n. If we go back to how we had defined this relationship for this linear map S relative to these E's, now anytime we see an E sub j, we can replace it with the scaled version in the same direction. And the scaling is this eigenvalue lambda sub j. Meaning this right-hand side now I can replace by lambda 1 VE1 E1, where I've simply replaced capital SE1 with lambda 1 E1, and lambda 1 is a scalar. I'm just locating it in front of that other scalar, which is the inner product of V with E1. Is that okay, what I'm doing? And I can just do that for all of these. If I now take the norm of SV and square it, do you see what it's going to be on the right-hand side? Now my coefficients that are scaling E1, I'm just going to take their absolute value and square it. And I'm actually going to separate that coefficient into two pieces, where the product of the absolute value is going to be the product of absolute values. I'm going to take lambda 1's absolute value and square that, and then multiply that by the square of VE1. Meaning I now have this lambda 1 squared VE1 squared plus lambda sub 2 squared VE sub 2 squared plus lambda sub n squared VE sub n squared. But if S is an isometry, then we have this relationship between its norm and the norm of the original vector V. What's that imply about all of these lambdas squared? They all have to be 1, don't they? Since this right-hand side in green needs to equal this right-hand side in green, and the only difference in that, in terms of that expression, are these lambdas squared. And the only way that the top right-hand side can be equal to the bottom right-hand side is for all of those lambda sub j squared equal 1 for all j. So there's one result. If we have an isometry, which means that the norm of SV is equal to the norm of V for all V, then we know that the eigenvalues of that operator are all 1. The other thing that we can observe, which is what I commented on when we were first stating the goals, is if S, this linear map, is an isometry, then S is injective because if SV equals 0, or because SV equal to 0 can only be true for V equal to 0, if SV is equal to V. Meaning if we have SV equal to V, the only way that that can be 0 is equal to 0 is if the right-hand side is 0, or the vector V is the 0 vector. If this relationship was true and the left-hand side was 0, then V would be in the null space of S, and it would have a norm that wasn't equal to 0. Meaning every isometry is injective, which, if it's an operator, means that it's invertible. So anytime you have an isometry, it's invertible. Consistent with that one theorem or proposition that had all of these equivalent statements, A through E, we can do the same thing for these isometries. We can start showing a long list of equivalences when we have some map that's an isometry. Long list of equivalent statements for isometries. And this is coming to us in the form of Theorem 36 in Chapter 7, which says, given S is a linear map or a linear operator on this inner product space V, the following statements are equivalent. First, S is an isometry. And that just means that the norm of SV is equal to V for all V in our vector space. That can be shown to be equivalent to SU, inner product with SV, is the same as the inner product of U with V for all vectors uv in our inner product space capital V. If S is a linear map, is an isometry, statement A, then S adjoint, or S dagger S, is actually the identity map. Another equivalent statement is if we now take SE1, SE2, and S mapping E sub n, that list will be an orthonormal list, is orthonormal whenever the original E's, E1 through E sub n, that list is orthonormal. So if we start with an orthonormal list, E1 through En, if S is an isometry, we're not changing the orthogonality of that resulting list, where S is now operating on all of those E's. Likewise, there exists an orthonormal basis E1, E2 up to E sub n such that SE1, SE sub 2, SE sub n is orthonormal. And I could just keep going with this equivalent list, but now what I would be doing is replacing in F through J the original linear map with its adjoint. So let me say this is F through statement J is the same as statement A through statement E above, except in statements F through J, we have the adjoint of S replacing the original map S. Or you could think of this as S and its adjoint, S dagger, are interchanged in statements F through J. And all of those are equivalent. If statement A is true, that's equivalent to statement F, etc. And we're not going to show that. So I'll spare you the details and I'll refer you to the textbook for the proofs of those equivalences, A through J. In summary, though, of what that theorem 736 says is that statement F would say that if statement A says S is an isometry, what does statement F say? S adjoint. The adjoint of that operator is also an isometry. And if you look at statement C, this says then that the linear map S, when we take the operation of S adjoint onto S, then that gives us the identity. Then S adjoint is the inverse of that map S. So the composition of S adjoint S, giving us the identity, says that S adjoint is actually S inverse. And that's from statement C. Likewise, if you look at statements B and its twin, statement G, then S and S dagger preserve inner products. Where B said if you now scale U and V with S, where S is an isometry, then you're going to get the same scalar out of SU inner product with SV as you get with the inner product of U with V. So S and S dagger, that was statement B. G is the equivalent one for the adjoint. They preserve inner products. And they also, if you looked at a couple of other statements, S and its adjoint preserve orthonormality. Which is statement D and I. Something else that we can notice by examining these relationships a little bit more is we learned that S dagger S was what? That's the identity, and that came to us from statement C. But we also know from its twin statement down below, which we didn't explicitly identify or write down, that's also equal to, now we would just interchange the adjoint and the operator with each other. This is now equal to S dagger. That's also the identity. That was statement H. But if S dagger S is equal to S dagger, what's another way of referring to S now? Or what's another label or defining term that S could be called? And S again was an isometry. So all isometries obey S dagger S is equal to S dagger, which is really saying that S and S dagger commute, which is another way of saying S is normal. So if we have an isometry, any isometry or all isometries are normal. Which is what that statement above says. S dagger S equaling S dagger is really just saying S commutes with S dagger or with its adjoint, or S is now normal. Suppose we look at theorem 37. This says for V, a complex inner product space and S being a linear map or a linear operator on that complex inner product space, S is an isometry if and only if there exists an orthonormal basis of this complex inner product space V consisting of eigenvectors of S with all corresponding eigenvalues lambda having a magnitude of 1. So if we have a linear operator that's an isometry, then if you find the eigenvalues and eigenvectors of that operator, the eigenvalues will all have a magnitude of 1, and the eigenvalue or the eigenvectors will form an orthonormal basis for that operator S. We earlier showed that if we had all of the eigenvalues equal to 1, then S is an isometry and now let's look at the other direction. Suppose we assume S is an isometry. We now know that that means it's normal. S is normal. And what do we know about normal operators from our spectral theorems? Now our spectral theorem says there is a basis of orthonormal eigenvectors for that normal operator. Or we can diagonalize that matrix. If that's the case, therefore, let each of these eigenvalues, lambda sub j, be an eigenvalue associated with E sub j. And let's just take the absolute value of lambda sub j. That's equal to the scalar lambda sub j E sub j. Since E sub j is normalized to 1. But lambda sub j e sub j, or the argument of that norm, is we just said that that e sub j was an eigenvector for the operator s, so this is now s e sub j. But if we're assuming that S is an isometry, what do we know about SV, where V is now E sub j? If S is an isometry, it's norm preserving, which means that this is E sub j. SV is equal to V in terms of norms. But what's the norm of E sub j? It's 1. And that's true for all j. And now we know that the eigenvalues of an isometry are equal to 1. That was for complex inner product spaces, the capital V. What about real spaces? And we know that a lot of times when we deal with real spaces, it gets a little bit more constrained as far as what we can state. Here's theorem 38 from chapter 7. Suppose V is now a real inner product space, and S is a linear operator on that inner product space. S is an isometry if and only if there exists an orthonormal basis of this real inner product space V in which this operator S, now if S is normal on a real inner product space, what did we say about the structure that we could have result from or in this real inner product space? Do you remember? We were talking about block diagonal, and we said, oh, if anything is normal, it can be block diagonalized. And if we were in a complex inner product space, those blocks were all 1 by 1, weren't they, on the diagonal? But now, with a real inner product space, we've learned that we can have rotations that do not have real eigenvalues, and that restricted these sub-blocks on this block diagonal to only being 2 by 2, or to, at the best, as small as they could be, as 2 by 2. Some can be 1 by 1. Meaning, on a real inner product space, S is an isometry, which means S is normal. And once we have S normal on a real inner product space, we know it's block diagonal. Block diagonal. It's not necessarily complete or true diagonal. It's block diagonal, in which S is block diagonal with blocks that are 1. We know the eigenvalues have to have magnitudes of 1, but minus 1 also has a magnitude of 1, so that could also be, so we could just turn around, essentially, in terms of rotation, or we could have a 2 by 2 subblock that has the structure cosine theta, sine theta in the first column, minus sine theta, cosine theta in the second column, where theta is some angle between 0 and pi. And the reason why I have that as an open left-hand parenthesis is if it was 0, then I really wouldn't have a 2 by 2 block. I would have two 1 by 1s. I would have a 1, 1, and I would have 0 off diagonals, and that would then revert back to having blocks of 2 blocks of 1, 1. Meaning the angle theta now is going to be something bigger than 0 up to pi. That's theta. That's theorem 738. We won't prove that. You're welcome. But you can look at that or look at that on your own. But what we want to do is look at the structure, what that means, to get a more intuitive feel for that result. We have these 1 by 1 blocks. That indicate these eigenvector eigenvalues, and lambda for an isometry, or the magnitude of lambda for an isometry is 1. If we're dealing in a real inner product space with 1 by 1 blocks, then our only option with real numbers is to have them equal to plus or minus 1. These 1 by 1 blocks for an isometry. If it's complex, then we just have the absolute value of those lambdas is equal to 1. For the 2 by 2 blocks, those correspond to two-dimensional or 2D invariant subspaces. Where you could think of rotation. Those we don't have to worry about 2 by 2 blocks if we're dealing with complex inner product spaces, but it's always a possibility for real inner product spaces. And those 2 by 2 blocks are really just a form of a rotation matrix. That was the sines and cosines. Which really says that these isometries, or the isometry, is a generalized rotation. Where we actually showed that the form must be A minus B, B, A, when we're dealing with a normal operator. And if we're playing with that, we actually need the norm of SE1, where E1 is an eigenvector. We need that to be 1. Meaning if we just looked at these 2D rotations, we now have a submatrix, let's say S, scaling E1 and E2, and what we're saying is that now is equivalent to this A minus B, B, A relationship. If we now do the multiplication on the right-hand side, remembering that E1 and E2 are column vectors, then we take E1 and scale it by A and add to that a scaled version of E sub 2, which is scaled by B. That makes up the first column. The second column is minus BE1 plus AE sub 2. Now, if we look at the norm of SE1 squared, that's now saying that we're interested in the norm of AE1 plus BE2 squared. But remember, E1 and E2 are orthonormal vectors, aren't they? And now A and B are just scalars. So that now we have the absolute value of A plus the absolute value of B squared, or if we're dealing with the real inner product spaces, that's now A squared plus B squared, and we want that to equal 1. And one way to make or to create A and B when squared and summed to equal 1, we could use A being cosine theta and B being sine theta, and that would produce what we need. So that's sort of this verification of this structure, AB minus BA, when we're dealing with real inner product spaces, or you could think of it as cosine theta sine theta and minus sine theta cosine theta. That's going to happen when we're dealing with real inner product spaces. If we're dealing with complex inner product spaces, we're going to have diagonal matrices, one by one submatrices. Let's now that we have positive operators and isometries, let's look at how we can think about that relative to decomposing a matrix or a linear map or a linear operator. We'll do that by remembering the analogy, or recall the analogy between operators and numbers. Where here, if I started with a complex number, let's say that's Z is C, what did we associate that with in terms of an operator? That's maybe a difficult question because that was just the generic linear operator T, a complex number. So we were associating a complex number with just a generic linear operator T, meaning if you want to boil something down and it's not making any sense with a linear operator, you go, let me just think about this like a complex number. What happens when I take a complex vector and scale it, operate on it by a complex number? What do I get? Well, that's sort of how you can think about a linear map. What's going to happen when you take a vector and map it through this linear map T? The linear map is going to be like what happens when you operate on a complex number with this scalar that's complex. That's one row of this table. What happens, or if a complex number, just a generic complex number, is associated with or analogous to a linear operator, what happens when we look at the complex conjugate? What is that analogous to in terms of a operator? So if T was like Z, then if I take Z star, what's that look like in terms of a map or a linear operator? That's the adjoint. So again, the adjoint is what happens, or what happens to this operator in the inner product when we slide it from the first slot to the second slot. And we would have to, because of the conjugate symmetry of the inner product, we'd have to make that, when we move a complex number from the first slot to the second slot, we would have to conjugate that scalar. Now, to do that with an operator, we now need to form its adjoint, or to put it, move it into the second slot of our inner product. What about if we now have a, in terms of a scalar, what if we have a real number? Let's say R. Well, in this case, Z is equal to its complex conjugate. What's an operator? Now we are saying that, oh, if we had an operator and it's equal to its adjoint, now we're saying over here in the operator side, that's what we were calling an operator that's self-adjoint. So a self-adjoint operator is like a real operator when we're dealing with this scalar version or its scalar analogy. What about if we looked at a non-negative real number? So that now Z is greater than or equal to 0, where Z is now real. So Z is equal to Z star is greater than or equal to 0. What kind of a map does that get related to? Now that's a positive map, isn't it? That's what we were calling a positive map, so that now T is positive, which is non-negative. Now if I said, what if we had a real number that was, or I'm sorry, a complex number whose magnitude was always equal to 1? In a two-dimensional setting, that's like giving us some angle. If we're on the unit circle with our number, now the magnitude is 1, but if you tell me where I'm at on the unit circle, I can understand the angle or the direction that you're making. Now that's like these isometries. We have all of these analogies. Let's now use those to inspire us into how to associate or think of these linear operators. Now we're going to be inspired by this analogy. Meaning, we can write any complex number or any complex number can be expressed in polar form. Meaning we can write a number z as z times 1, where my 1 is going to be the absolute value of that complex number divided by the absolute value. But now let me just rearrange some of those expressions so that I now have z divided by its absolute value times the absolute value of z, where this quantity and another way of writing the absolute value of z is to say, oh, take the square root of z with its conjugate. Or let me do it the other way around because that will be consistent with what we're doing with our operators. This, where is that relative to someplace in the complex plane? Z divided by its amplitude or by its magnitude. That's a normalized vector if it was in two-dimensional in the complex plane, or this is now corresponding to a direction. And this is just a length. So now this representation of a complex number is going to suggest a way of decomposing a linear operator. Would suggest that any operator, let's say T, on this complex inner product space V can be written as, now T we are going to write as a direction S. That's our isometry. That's like this Z over its magnitude times the square root of T dagger T. Here is now our direction, and this is our length, with S an isometry. Remember, T dagger T is what in terms of an operator? What kind of a property can you say, or how can you describe T dagger T? What do you know about T dagger T? Can you make any claim about T dagger T? And remember, that's analogous to Z star Z, Z conjugate Z. What happens when you multiply Z conjugate A minus JB times A plus JB? You get A squared plus B squared. You get a non-negative number. So T dagger T is a positive operator, and we just showed earlier today how to make that find the square root of that. So this is now the length or the scaling, and S is an isometry, the direction. We're going to create then or decompose, and this is what's called the polar decomposition, which is theorem 41. We are going to now be able to decompose a generic operator into this polar decomposition, which is a scaling and a direction or rotation. And that's where we'll pick up on Monday.